Just give you a little formal introduction. We got Lucas Castillo here as a PhD student from the University of Warwick, as you can see here, to give us a talk called Human Random Generation as a Locally Bound Process. Lucas, you can take it away.
Right, thank you. I'm gonna give a talk on human random generation, and I want to say thank you for inviting me to do this. And this is work I'm going to present that I've done in collaboration with Pablo León-Villagrá, Nick Chater, and Adam Sanborn from the University of Warwick and Warwick Business School. And I wanted to start by talking about the role of randomness in cognition more generally, and just wanted to talk a little bit about early work that was done by people such as Baddeley or Kahneman and Tversky, who viewed people as intuitive statisticians, much like we do today, who go about their lives making inferences. And so because randomness is such a central component of statistics, they thought, well, let's find out how people generate these random sequences, or whether people can judge sequences to be arising from a random process or not. And people don't do this very well. They found that they make systematic errors. And so I'll talk about them a little bit later, but I just want to point out now that there's this kind of apparent paradox that people are very good at the statistics of the environment they're in, but their concept of randomness, or their ability to generate or perceive things as random, is not very good. The other role that I think randomness plays is a little bit more low level, and it's that randomness features quite importantly in a lot of cognitive models. So like the ones on screen, and the reason for this is that you need some sort of stochastic component to a cognitive model a lot of the time to account for the fact that people behave differently faced with the same situation, that people are inconsistent with themselves. So for example, in Nosovsky's categorization model, the person will have learned categories and will have calculated the similarity of an item with categories that they've previously learned. But the actual categorizing moment will be done according to a probability distribution. And in that moment, you just draw a random sample, toss an imaginary coin, and choose one category or the other. So this random sampling also features in cognitive models as well. And so there's another paradox here of we saying that people can generate randomness when they categorize or they make perceptual decisions, but when we explicitly ask to generate random items, they're not very good at it. So I'll just focus on human random generation, and I'll describe the number random generation just because it's the most popular task. And people systematically deviate from this random or independent identically distributed sampling when producing random sequences. So one of the things that they do is that they make too few repetitions. So in this example sequence, there's only one, that too many items are adjacent to the previous item, and that there's too few turns. So these participants engage in this long ascending or descending runs, like the ones you see on screen. And so every time you change trajectory, you can call this a turn. And compared to a random sequence, people make fewer turns. And so you can try to model this and try to explain what people are doing, because they're not drawing random samples. What are they doing instead? And the most prominent account of random generation is this schema account, which is maybe studied by Baddeley back in the day. And it's this idea that what you are doing when you ask to generate random items is to use these pre-learned schemas or policies. And these are just some examples, but it doesn't have to be this. So Cooper 2016 proposes that you just have from -5 to +5, and you just choose one. But you could have others like going from the boundaries to the center or anything else. Yeah? And what you do is that you apply the current schema that you have chosen to generate an item. And once you've generated the item, you judge the randomness of your sequence. And so if you feel that you're all good, you keep going. If you feel that your randomness is declining, that you've been using this strategy for too long, then you have to change your schema before you keep going. And this changing process might have some memory components. So you might have some sort of recollection of schemas that you've used recently so that you don't use them again. and you might have some bias. So you might prefer some policies to others. And this account has been successful at explaining these global deviations from randomness that I was explaining before. So looking back at these three signature behaviors, we can see that these few repetitions or too many adjacent items can be thought of as biases that people have against the +0 or the ±1 schemas, respectively. And you can think of this absence of terms or this tendency to keep trajectories as these infrequent schema changes. So the person's doing +2 a lot, and then they don't change often, and then you're going to have consecutive items that share a similar direction. And this approach has also been successful at explaining the how people get worse at generating random items under cognitive load. So there's a long tradition of giving people very little time in between items, or asking people to do something else while generating random items. And when they do this, obviously they get worse. But we wanted to propose an alternative account of how people might be generating items that's a little bit more general. So instead of proposing a separate mechanism for the generation of random items, instead we propose that people are tapping into a general cognitive ability that they use to produce samples for probabilistic inference. So this sampling for probabilistic inference, this is a computer science technique that it's used to approximate Bayesian inference, which is intractable. And so when you don't know your posterior distribution, you can use these local sampling algorithms to generate items from this posterior distribution, and that way create a kind of approximate histogram for you to calculate the probability of something. Because humans also have to approximate this intractable Bayesian inference, or they seem to be doing this, this has been used to explain deviations from probabilistic, optimal probabilistic reasoning that people make, which under bounded rationality, or when you cannot draw many samples, you might lead to these deviations that we see in people, such as the anchoring effect and others. So I'll just explain how a local sampling algorithm works in very broad strokes. So basically what you do is you choose a starting point, and then what you do in every iteration is very simple. You just choose a new point, and you compare the density of the current and the new points, and then you move to a new point with probability proportional to the ratio of the densities. So that way, all you need to do this is to be able to calculate the density, or at least to be able to compare the densities between items, but you don't need to know the shape of your posterior distribution. So I've just have an example here with a normal distribution. So you have a starting point, and then you choose a new one, you compare the densities, and you choose to move or not. In this case, the point you started at is better than the other one, so you're going to be a bit reluctant to move. And in this case, the sampling algorithm doesn't. And then you propose a new point, you compare the densities, it's going up, it always goes up, it always goes up. And then sometimes when it goes down, it's biased toward moving, so it will go down. And I'll stop now. I won't show you any more iterations, but if I were to continue this for 1,000,000 times, you would eventually get a histogram that is identical to the normal distribution without ever having to know that this is a normal distribution. So going back to this idea of random generation, in which the shape of the distribution is not normal, but it's uniform, you already might already intuitively be able to see these signature deviations that we were talking about in people. So because you're proposing nearby points, you might have items that are adjacent to the previous items. Because the posterior distribution is flat, all your purple arrows are horizontal, so you're always going to accept the proposals, which means that you're always moving, or you're very unlikely to repeat an item. And if you were to have some sort of proposal policy that, or proposal approach that has some sort of memory of where you've been, or that likes to not backtrack very often, you would also find this idea that there's fewer terms. So just to summarize, there's these two accounts for random generation that I've described. The schema account is these pre-learned policies from associations you have between items, whereas the sampling account cares about the topology of the space. And unfortunately, with the number line, with random numbers, it's very difficult to tell them apart because you need a task where associations between items are disentangled from the topology of the space, which is not the case in random number generation. In random number generation, the associations between number exist prior to the task. So I could say my phone number in the task, and you wouldn't know that that's not random. And also that the domain that you have to randomize from is always one-dimensional, and it's always a sequence that you've learned in a very particular way. We've all learned the numbers from 1 to 10, right? I think. And so we created a new task that aims to overcome these problems. And so in here, instead of numbers, people learned a display in which they had to learn a display with meaningless syllables that had different global arrangements. So some people learned this representation one-dimensionally, some people learned it in 2 dimensions, and they also had different local arrangements. So the order of the syllables within the display was 1 of 5 possible random arrangements according to 4 different participants. And so the procedure was that people learned 1 syllable at a time, and then we tested that they had learned them correctly. And then they had to say syllables at random for 5 minutes at a pace of 80 items per minute, crucially without seeing the display. Instead, what they saw was a flashing dot on the screen to help them keep the pace. And they did this twice, but both of the times was with the same display. So we had 2 sequences per participant from the same displays. And looking at these descriptive measures that we're talking about, a sanity check would be to look at these repetitions, adjacencies, and turns for this task. And the patterns that we see are the same as in random number generation. So that's good because it means they're doing kind of the same. So there's fewer repetitions than expected from a random or independent identically distributed sequence. They have more adjacencies and they have fewer turning points. And then what we did was compare the proportions for participants in the 1 and the 2-dimensional condition. So participants that had learned this 1-dimensional display or the 2-dimensional display. And we did this by calculating a difference score. That was the log observed proportion minus the log expected proportion from a random sequence. And although we saw no difference between the repetitions, we did see that participants in the 1-dimensional, who had learned a 1-dimensional display, made more adjacent items and fewer turns than those in the 2-dimensional condition. We also looked at the temporal component of these utterances that people were making. So even though we asked people to do it at 80 items per minute and we gave them the flashing dot, people don't always respect dots on screen. And so they might have more, or they might take longer to say something or less. And so we performed a logistic regression calculating whether something would be a repetition or an adjacency and so on based on the delay from the previous syllable. And we found that people are more likely to make a repetition the longer they take between items. They're less likely to make an adjacency the longer they take between items, and they're more likely to make a turn, which kind of is consistent with this idea that people are traveling this mental space, and the longer they take before their next item, the further they are from the starting point, the more likely they are to have changed trajectory or traced back on their steps. Finally, we made some models that predicted each syllable condition on the last 2. Previous work on random generation has mainly focused on descriptive at the global level, like I've been describing so far. But what we did was compare models that predicted the likelihood of a syllable at a time. And so these were conditioned on the last 2, which meant that if a participant had said na and they had said la, then that's all the model would know and would calculate the probability of each of the 7 possible syllables. And then if the person says ha, then the model forgets that you ever said na and just looks at this information to make the predictions. The 2 models were, one of them was a schema model, which was, as I said before, based on like these pre-learned ideas, and the sampling model, which was based on the topology of the space. And these 2 models were composed by 4 model parts rather than a single block. And the likelihood of a syllable was calculated as the weighted sum of these model parts. So I will explain now what those model parts were. And I'll do this with an example for each. And just remember that we're looking at a person that has just said na la, and now what does the model part predict, right? So for the sampling model, which is this model that cares about the topology of the space, there was a proximity model part that cared about the Euclidean distance from the last syllable to the possible next. And so in this example, la is 0 distance away and everything else is 1 away. So la is given more probability. The inhibition of return model part just cared about you not backtracking. So it would inhibit the second last syllable. No repeat is self-explanatory. And then the momentum model part gave probabilities based on the trajectory you were keeping. So in particular, like how much of an angle deviation you would have from your current trajectory. So if you said na la, then ha is 0 degrees difference. So that is the most likely, whereas ka is 120. So that is more likely. Whereas the schema models cared about pre-learned ideas before the thing. So it cared about how frequent these syllables or pairs of syllables, these are unigrams or bigrams, are in the English language. So the syllables are pretty much all the same. The bigrams, well, the la-na bigram seems to be more frequent in the English language. And then how frequent the syllables or the pairs of syllables had been in the learning sequence. We compared how successful each model was for each sequence. Each column is a participant. Each row is one of the 2 sequences that the participants made. And we can see that the local sampling model was the most successful model, especially in the 2-dimensional displays. And we can also see that people are in general quite consistent with themselves in the way that they generate random items. And an advantage of this weighted sum approach was that we could then calculate the contribution of each model part. So we looked at this local sampling model that had been the most successful, and we found that the no repeat and momentum model parts were the parts that carried the most weight. And so just to conclude what this experiment, the conclusion from this experiment is that the topology of the space influences the ability to produce random sequences. We saw that some of the descriptives, such as adjacencies and turns, were different according to the whether it was 1 or 2-dimensional. We saw that the temporal information was consistent with this idea that people are navigating this mental space and that they travel further the longer they take before the next item. And the models told us that this repetition and momentum are key features of this random generation process. So I'll just finish with some current work that we're doing. Most work on random generation has mainly focused on uniformly distributed variables, but our more general approach predicts that people can also draw random variables that are non-uniformly distributed. So an experiment we just finished running, we asked people to say random heights from a target gender, male or female, and so they either did so from the population in the UK or from an artificial distribution that is uniformly distributed. And you can see that people kind of more or less approximate them. And the other thing we're kind of looking at is trying to formalize which sampling algorithm explains best what people do when generating random items. So, and one of the signature behaviors we're looking at is the position in the distribution in which people make the turns. So in here, what you can see is the proportion of abrupt turns according to the position in the uniform distribution. And you can see that at the boundaries, obviously people make more turns because there's nothing else to do because you've run out of space. But in the middle, the proportion of turns is below 50%, which is not what you would get from a random walk or from IID sampling. So that kind of tells us again that there's this kind of tendency to keep one's trajectory. And so sampling algorithm.
Lucas, hey, I don't want to rush you. I know you started a few minutes late, but just to make sure we can fit in some questions and still
I have 1 minute left. Can I do that?
Yeah, go for it. I was going to say let's wrap it up in like 2 or 3 minutes.
That's fine. Thank you for that. Yeah, so I was just saying that being drastically below 50% indicates that these people are not, the sampling algorithm is not a random walk, because it would be 50% otherwise. And so it has this idea of keeping trajectory, or having this sense of recycled momentum that can explain this. So just to finish, I wanted to look back at the schema account, and this is the same image I showed before. What I've proposed today is that instead of applying the current schema, people might be sampling locally to generate these new items. But I also wanted to, as future directions, kind of point out other directions that are interested in the current schema, which is, for example, the fact that people still might be monitoring the randomness of the sequence. And so that would be an interesting addition to our current approach, or that they might be tweaking the generating process. So some sampling algorithms are what they call adaptive, in which that they change the parameters of sampling as they progress, because they track how well they're doing. And so these are future directions forward. If you're interested in the sampling approach to Cognition, there's this website you can check with the group. And that's it from me. Thank you very much for listening.